Imagine you're tasked with building like a massive commercial airplane. You spend months wiring the avionics, calibrating the altimeters, bolting on the jet turbine.
Right, a massive engineering project.
Exactly. But then right before the maiden flight, you just toss the keys to the pilot and say, hey, we never actually verified if the wings are structurally sound, but the engine turned on. So looks pretty good from here.
Yeah, I mean, you would never put a human being on that plane.
No, never.
Because a catastrophic structural failure is essentially guaranteed at that point. In the physical world, doing engineering without rigorous, isolated testing is, well, it's considered malpractice.
Cool.
Yet in the digital world, writing thousands of lines of logic without unit testing is the exact equivalent. You're basically building the fuselage, crossing your fingers, and just hoping the wings don't shear off at 30,000 feet because of some, unforeseen edge case.
And that is exactly what we are getting into today. Welcome to the deep dive. If you're someone who loves gaining thorough technical knowledge without the crazy info overload, you are in the right place.
Absolutely.
Today, our mission is to unpack a really fascinating stack of source material, all about an introduction to programming with Python unit tests.
It's a great topic.
It really is. We're going to trace how developers actually verify their internal logic, moving from like the most basic native truth-checking commands, scaling up through external frameworks, and finally looking at how the system organizes everything when your code base inevitably gets huge.
Yeah, and this progression is so cool because it perfectly illustrates how a code base matures, We're moving from fragile, isolated scripts into these robust, verifiable software architectures.
Right, turning that sketchy airplane into a fully certified jet.
Exactly. And to really understand how those ecosystems operate, we have to start at the absolute bedrock of how Python handles internal assertions of truth.
Okay, so where do we start?
Well, before we introduce complex external tools, we have to look at the native keyword built directly into the language, the assert statement.
Ah, assert. It gets described casually as a sanity check a lot.
Yeah.
But structurally, it acts more like a really strict circuit breaker for internal state, right?
That's a perfect way to put it. You basically feed the assert keyword an expression.
Okay.
CPython evaluates that expression, and if it resolves to a truthy value, execution just flows silently right to the next line.
It's like a strict bouncer at a club. If you're on the list, you just walk right in, no drama.
Yes.
Yeah.
But if it evaluates to false, it trips the breaker. It raises an assertion error exception and instantly halts the entire execution thread.
The bouncer just shuts down the whole club. But wait, is completely crashing the program with an assertion error really the best way to handle things? I mean, for a user, that's an awful experience.
So that's a really valid pushback.
Yeah.
And it requires us to distinguish between expected runtime errors and internal logic errors.
Okay, what's the difference there?
So if you're building a system and a user might say, input an invalid email address, you don't use assert for that.
Right, because you kind of expect users to make mistakes.
Exactly. You use standard flow control for that, like a try except block, to catch it and return a nice helpful message. You want the system to fail gracefully.
Because crashing the whole app just because someone forgot the @@ symbol in a form is incredibly hostile.
It's the worst. But an assert is not for the user. It's strictly an internal contract between the developer and the machine.
Oh, okay.
It's defensive programming. You use it to verify invariance. Those are conditions that absolutely must be true for the rest of your math or logic to be sound.
Give me an example of that.
Like if a physics engine calculates gravity and somehow returns a negative integer for mass.
Oh, yeah, that breaks the laws of physics.
Right. The internal state of your app is completely corrupted at that point. In that scenario, trying to fail gracefully or recover is actually the worst thing you can do.
Because if you keep going with corrupted data, you'll write bad data to the database or cause some massive cascading failure miles down the road.
Exactly. You want it to fail fast and fail loud.
You want the circuit breaker to kill the power the exact millisecond the voltage spikes so you can see exactly where the fire started.
That is the core philosophy. You want that assertion error to stop the world so you can inspect the exact conditions that broke your contract.
Makes sense.
And in fact, Python's bytecode compilation proves that assertions are purely developmental tools.
Wait, oh.
Well, if you run a Python application and pass the asho flag, the optimize flag, to the interpreter, it sets a built-in constant called debug to false.
Okay, and what does that do?
When that happens, the interpreter completely ignores every single assert statement. It literally strips them right out of the generated bytecode.
Well, really? It just deletes them?
Yep. They vanish.
That is a crazy critical detail.
Hmm.
I mean, imagine if you were improperly using assert statements to check user permissions or validate secure payloads,
Oh, it happens.
and then a DevOps engineer deploys your code to production using that optimized flag. All your security checks just disappear.
Instantly vulnerable, which really enforces the rule. Assert is an internal diagnostic tool, not application logic.
Right.
But while native assert statements are great for those baseline truths, they become a massive bottleneck when you try to build a real testing suite.
Because, well, think about it. If we have a file with 100 assert statements and the very first one fails, it raises the error, the thread dies, and the other 99 tests never even run.
Exactly. It's a painfully linear process. You fix the first bug, run it again, and then it hots on the second one.
Plus, a native assertion error doesn't actually give you much context, right? It just says it failed. If I have assert user count equals 5 and it fails, it doesn't tell me that the count was actually 12.
Right, it drops its internal state.
Yeah.
And that lack of introspection is exactly why our source material immediately pushes us to graduate from those native built-ins.
We need an upgrade.
We do. And that brings us to PyTest.
Okay, so the source specifically points to the command pip install PyTest. It's like we're realizing the flimsy manual screwdriver that came with the furniture isn't enough, so we're going to the hardware store to buy a professional power drill.
That's a great analogy. We are using Python's package installer to pull down a professional testing environment.
But what I find fascinating is the actual mechanism here. We aren't just downloading a script that runs our files in a loop, are we?
No, not at all. We are fundamentally altering how the Python interpreter processes our test code.
How does PyTest solve that introspection problem then? Because other frameworks, like the built-in unit test, force you to use weird syntax like self.assert equal AB.
Right, they have to do that to capture the values of A and B so they can print them out when it fails.
But PyTest doesn't do that. You just write the normal native assert A equals a B.
Right.
Yet somehow, when it fails, you get this beautiful, rich, color-coded report telling you exactly what A was and what B was.
Yeah, it's pretty amazing.
How does it extract that context if the native keyword drops it?
It uses something called abstract syntax tree rewriting, or AST rewriting.
Okay, AST rewriting, walk me through that.
So when you execute the PyTest command, it doesn't just pass your files to the CPython interpreter normally. It registers a custom import hook.
Okay.
And before a test module is fully loaded and compiled, PyTest intercepts the source code.
Wait, it grabs the code before Python even runs it.
Exactly. It parses the plain text of your Python file into an abstract syntax tree, which is basically a structural representation of your code's logic.
So it's actively reading and mapping the file out.
Yes, it traverses that tree, and every time it finds an assert node, it dynamically rewrites the tree.
It rewrites your code.
Yep. It replaces your simple assert A equals using B with a huge, complex block of introspection code that evaluates A, evaluates B, stores their values, does the comparison, and then if it fails, packages all those stored variables into that highly detailed report you mentioned.
That is architectural magic. So as a developer, you get the clean, readable experience of writing native Python. But under the hood, PyTest is basically acting as a lightweight compiler extension.
Exactly. Injecting telemetry right into the bytecode.
So when the circuit breaker trips, it sends a full diagnostic snapshot back to the console.
And this is key. It catches the exception. Instead of the error halting the entire process, PyTest traps it, logs the snapshot, and cleanly moves on to the next test.
So you run one command and get a report of every single pass and failure across the whole system.
And at once.
But because PyTest is doing this heavy lifting, the AST rewriting, trapping exceptions, its capability set is massive, which brings up an interesting point from the source.
Ooh.
The source doesn't just say install PyTest. It explicitly directs you to docs.pytest.org.
Yes, it does.
And for someone scaling up, having to constantly reference an external manual, I don't know, it can feel like a failure of intuition.
Yeah.
Does relying so heavily on documentation mean the framework is just too complicated?
I'd argue it implies the exact opposite.
Yeah.
Yeah. Pointing to the documentation highlights a necessary shift in how modern developers manage cognitive load.
How do you mean?
When you pull in a tool as powerful as PyTest, you're essentially learning a domain-specific language, a DSL embedded inside Python.
Right.
PyTest handles all sorts of complex stuff: test parameterization, custom markers, dependency injection through fixtures. You cannot, and honestly should not, try to hold that entire API in your working memory.
So it's a shift from rote memorization to, like, index knowledge.
Precisely. You don't need to memorize the exact syntax for yielding a database connection in a fixture. You just need the architectural awareness that fixtures exist.
You just need to know what it can do, and then you use docs.pytest.org to index the how when you actually need to type it out.
That's the mark of a mature engineering mindset. Framework documentation isn't a crutch for things you forgot. It's the operational manual for heavy machinery.
I love that. You consult the manual because the tool operates with extreme precision. You offload the syntax memory so you can focus on the actual logic of your tests.
Exactly.
So, okay, we've upgraded from raw assertions to this sophisticated framework that rewrites our syntax trees. We're using pip and referencing the official docs.
Yeah.
But as we write more tests for our databases, our APIs, our data pipelines, the raw number of files is going to absolutely explode.
Oh, it will, and that becomes an infrastructure problem.
Right. You're no longer just managing a script. You're managing a massive file system hierarchy.
And if that hierarchy isn't structured in a way that the Python interpreter explicitly understands, your advanced testing framework will completely fail to run.
Which navigates us perfectly to the final structural components of our source material, packages,
Yeah.
and the init.py file.
The organizational layer.
Right. Because from a pure file system perspective, a package is literally just a folder with some Python files in it.
On the hard drive, sure. But to see Python, a directory isn't inherently a namespace.
And if PyTest is crawling our huge project looking for test files, we need a way to bind those physical folders into logical namespaces.
Right. To understand why init.py is so critical here, we have to look at Python's module resolution algorithm.
Okay, let's break that down.
When PyTest runs, it uses heuristics to find your tests, usually looking for files that start with test. But finding the file is only half the battle.
What's the other half?
To run the test, Python actually has to import it into its internal sys.modules cache.
And this is where namespace collisions cause those silent catastrophic failures we hear about.
Oh yeah, they are a nightmare.
Imagine this. You have a complex project. You have a folder for user logic and a folder for admin logic. In the user folder, you have a file called testauthentication.py.
Oh.
And in the admin folder, you also have a file called testauthentication.py.
Right, very common scenario. If those directories are just standard folders without an init.py file, they aren't registered as packages.
So what happens?
When PyTest attempts to import the first file, it loads it into the global namespace simply as test authentication.
Okay, so the first one works.
But then it navigates to the admin folder and tries to load the second file. Python looks at the namespace, sees test authentication is already loaded, and it either throws a weird import error, or even worse, it silently skips the second test file entirely.
Because it just assumes it already ran it.
Exactly.
So you'd have this massive blind spot in your test coverage, all because of how the interpreter resolves names. So how does init.py fix this?
It acts as a structural flag. It intercepts the module resolution process. When Python sees an init.py file inside a directory, it basically says, do not treat this as a standard folder. Bind this directory name to the current namespace.
It turns a physical folder into a structured Python module.
Yep.
But wait, from what I understand, this init.py file is usually completely empty, literally 0 bytes of data.
Yes, often it is.
We are so used to thinking of code as instructions that we explicitly type out. But here, the mere presence of an empty file is the instruction.
Isn't that wild? It alters the state machine of the interpreter. With an empty init.py file in both the user and admin directories, Python binds them properly.
So the first file gets imported as user.testauthentication.
Right?
And the second is admin.testauthentication.
Exactly. They now have completely distinct, fully qualified identities within the cache. There's no collision. PyTest can safely execute every single test.
So the init.py is basically the routing table for the testing framework.
That's a great way to put it.
It really proves that in software engineering, physical file organization isn't just an aesthetic choice to keep your workspace tidy. It's a fundamental machine-readable requirement.
Without those files establishing boundaries, the tooling just cannot navigate the ecosystem.
And that really ties this whole progression together, doesn't it? The evolution of a developer's toolkit is basically an ongoing effort to manage complexity.
It really is. You start with the localized complexity of verifying a single variable, using the built-in assert statement to enforce a contract.
Right. Then you manage the complexity of diagnostics by bringing in PyTest to rewrite your syntax trees and trap those assertions.
And finally, you manage the complexity of scale by using packages and init.py to rigidly structure your namespaces.
So the interpreter can run thousands of tests without crashing into itself. It's the invisible scaffolding of the digital world. Whether you're making a small web app or the flight control software for that commercial jet we talked about.
This architecture is how engineers guarantee that the logic holds under pressure. It's how we verify the wings are actually bolted on.
And it forces a discipline of continuous verification. A robust test suite doesn't just prove your code works today.
Right. It proves that when someone else changes a core component 3 years from now, they haven't accidentally broken something miles away in the dependency graph.
Absolutely. But, as we close out this deep dive into all this verification architecture, there's a fascinating paradox embedded in this whole methodology.
Oh.
Yeah, a meta question about reliability that I think engineers have to constantly wrestle with.
I think I know where you're going with this. The problem of recursive trust.
Exactly. We've spent this entire deep dive establishing how we write complex, sophisticated unit tests to verify that our primary application logic is structurally sound.
We write code to test our code.
Right. But those unit tests themselves are just more code.
Yep.
They're logic written by humans, susceptible to the exact same typos, the same logical fallacies, the same oversights.
They absolutely are.
So if we are relying entirely on the unit tests to tell us our application is safe, who tests the tests?
Oh, man. That is where the architecture pushes into even deeper territory. Things like mutation testing, where you use automated tools to deliberately inject bugs into your main code just to see if your PyTest suite actually catches them.
Wow, so you actively break it on purpose?
Yeah, because if the framework injects a massive bug and your unit tests still pass, you suddenly know your tests are fundamentally flawed.
You literally have to engineer systems to verify the verification systems. It's an endless pursuit of structural truth.
It never stops.
Something to really ponder the next time you board a commercial flight, trusting those invisible layers of logic keeping you airborne. Thank you for joining us on today's deep dive.